a whole problem with a structure where we have to use rotation matrices. And yeah, let's do it. Well, let me first do one with, let me do a simpler one where we can just focus on the rotation matrix and stuff. So let's say we have a beam like this. Let's say this angle is 45 degrees. And it's leaning against a wall up here. And we'll put a horizontal force here of 200 newtons. And let's say that the mass of this beam is 10 kilograms. Make the length 1 meter. Let's make it a little bigger. 1.2 meters. How about? And we want to calculate the internal loads. Okay, so the first thing we have to do is calculate the external loads. So we have a force RA, an unknown vector there. And at the center, we have a 200 Newton force. And at the center going down, we have a force of 98.1. And then we have a horizontal force here. I'll call that RB. RBs. Rho, force, moment. I'll put my about point here. And so the first one is RA. The rho vector is 0. The force is RAX, RAY. Moment is 0. Then I'll go up to RB. So that is a rho vector of negative 0.849, positive 0.849. The force vector is RB0. And so the cross product is negative 0.849 RB. And then at the center, since these are at the same spot, I'm going to just lump these into one force. We have a rho vector of negative 0.424, positive 0.424. Since that's at the midpoint of these other 2 points I already did, I can just divide, just take the average of those two to find the rho vector of the one in the middle. So that's what I did there. This force vector is negative 200, negative 98.1. And the cross product is positive 126.39. So our first equation says RAX is equal to RAX plus RB is equal to 200. Second, RAY is equal to 98.1. And third, negative 0.849 RB is equal to negative 126.39. So RB is 148.87. RAY is 98.1. And $51.13?
Sure.
Okay. Okay. So there we go for the external loads. Now to calculate the internal loads, we're going to need a new coordinate system. And I do want to point out, so we want a coordinate system with the x-axis along the long axis of the member. Okay, there's always two options for that. We could do kind of turn ourselves mostly upside down and use a coordinate system like this. Or, you know, in this case, most people tend to just use whichever one is closest to our old coordinate system. But there will be some questions, and in cases where the thing is vertical, you know, like there's no use whichever one. Will your functions look the same if you do that? This is sort of a weird. So what if half the class did this coordinate system and half did this coordinate system? Would you get the same internal load functions?
Wouldn't they be the same but from the other side?
Yeah, so that's kind of what would happen is like x equals 0 means x equals 1.2 and the other one, you know. So point by point, those values would match, but the functions won't look the same. Okay. All right, well, I'm going to use a coordinate system like this, as you might imagine. I guess that's not a good place to put it. Okay, so here's the beam. Let me write out everything we know. So RA, we have a vector of 51.13, 98.1. RB is 148.87. We have a 200 Newton force here. But remember that weight force is a distributed load. And so we have a weight force of 98.1, and that's spread out over 1.2 meters. And so we have a downward distributed load. I'm going to just draw it like this. Of 81.75 newtons per meter. Okay. My phone is getting super hot in my pocket for some reason. Stupid entropy. And so now one by one, we got to go through these loads and re-express them in the new coordinate system. And the new coordinate system is going to be this. So our rotation matrix has to go from this to this. And so what's that angle of rotation?
Minus 45.
Yes, exactly. So that's clockwise, so you got to go negative. Theta is minus 45. You could also go positive 315. And so our rotation matrix is cosine of negative 45, sine of negative 45, negative sine of negative 45, cosine of negative 45. Plug those in and you get 0.7071, negative 0.7071, positive 0.7071, positive 0.7071. Okay? So one by one now, let's go through these vectors. And when we get to this, one, this distributed load, we're going to think of this distributed load as a vector that's equal to 0, negative 81.75. Yes?
Is it going to change your numbers at all if you picked the force on the ground to rotate it?
The force on the ground. Say that again?
If you had chosen RA as the center and rotated it counterclockwise?
Yes, it will change the matrix. Yep. Then, I mean, you can imagine we'd be mostly upside down, so that distributed load vector would be pointing up.
Oh no, if you had rotated the same direction, just chosen the opposite end as your origin.
Oh, okay.
So you still have the 200 facing down.
Okay, the other end is your x equals 0. Okay, you also want to have your x equals 0. Yeah, like you don't. So if you took this coordinate system and just put it here, then your x's would be going from 0 to negative 1.2, which we don't want to do.
Well, these are just forces, right? We don't have any lengths coming in.
Right. I mean, no, you can think of it that way, sure, for the rotation matrix, yes. But then everything would go haywire once. I mean, you could follow it through carefully and do it, but you wouldn't want to think of your origin here and go from x equals 0 to x equals negative 1.2. It would just look ugly. It's perfectly mathematically fine. Like if you hated your boss and like you could do it that way to get back at your boss, but what? Yeah, exactly. So I mean that's something to keep in mind, I guess, save for the right moment. But okay, so but yeah, all that matters for the rotation matrix are angles. So let's start with the 148. So we have 0.7071 minus 0.7071, positive 0.7071, positive 0.7071. And we're multiplying that times 148.87 in the positive x, 0 for y.
105.267.
What is it?
105.267.
Okay. And then what for y?
Same.
Oh, yeah. Okay, and this one's newtons. And that's going to be at our left end of our beam. So look at that and make sure that makes sense. When we express our beam in our new coordinate system and just think of it as horizontal, this is going to be the force on the left end. Now let's go to the 200. So this matrix is Q. I'm just going to keep multiplying this Q. So our 200 Newton force is negative 200, 0. And
Minus 141.4 in both.
okay. And then, well, this force RA, we might as well do it, but that's not going to come up in any of our cuts because that's going to be at the far right side, and the far right side never shows up in any cuts. But Q times, what was that force?
51.13, 98.1.
51.13? Okay, and what do you get for that?
Minus 33.2, positive 105.5.
And now the last one we have is the distributed load function. And so Q times 0, negative 81.75.
57.81
Okay,
and minus 57.81.
and this one's in newtons per meter. Okay, so now I'm going to redraw this free body diagram. On the left endpoint, we have a force vector of 105.27, 105.27. I wouldn't waste the effort like drawing the directions of these components and stuff like that, or drawing or approximating the direction of that vector or anything, because you're just going to be using vector components for your calculations. So you might as well just put this in like this. Then at the middle, we have a force of negative 141.20, was it? Dang it. 0.40, negative 141.40. And then over here,
It's actually 4.2, but
okay.
I led you astray.
I was wondering how those were all coming out.
I know, I just stopped giving you the 100.
Okay, I'm going to put these in here.
Yeah, we don't think it's direct all of your answers to no decimal places.
Yeah. I mean, the best way to go is to keep as many decimal points as you can handle keeping, and then round off at the end. You know, that's what a computer program would do too. So over at the right end, we have 57.81, negative 57.81. That one's not going to come up into our calculations. And then we have the weird new part. So the distributed load. Oh, damn it, I did the wrong one. This isn't going to come up, but this is the distributed load. The one we want at the end is the negative 33 point. Okay, what's that decimal?
0.21
Okay.
and 105.52.
Okay, 0.21 and 105.52. And now we're going to the two distributed loads. Okay, so for the distributed load that's now horizontal in our coordinate system, we have one going this way at 57.81 newtons per meter. And for the vertical component, it's going down in our new coordinate system at 57.81 newtons per meter. Okay, how many cuts do we have to make here? Well, besides the endpoints, we have one of these cutoff points. Remember, you need a cutoff point anywhere the distributed load function changes or anywhere you have point loads. Here's a point load. The distributed load functions are the same the whole way. So cut 1. Is for x's between 0 and 0.6. We have the force vector of 105.27, 105.27. We haven't gotten to the point load in the middle yet. And our distributed load functions, well, those are uniform, so they look exactly like these. So I'm just going to go right to treating these as point forces. Okay, so we have a point force to the right with a magnitude of 57.81 times x. And then we have a point force going down that has a magnitude of 57.81 times x. And then we have the internal loads. And this horizontal function of x is why, for the first time now, we're going to see internal tensions that depend on x. Okay, you can imagine, like, think about how, like, based on, like, this pin joint at the bottom has to support a lot of weight up at the top. And as you go, well, I said that wrong. It's not the pin joint. It's like, if you think of x, like material close to this pin, it has to support a lot of this beam's weight, okay? If you think of an x value way up here close to the wall, it only has to support a tiny little amount of weight. So we would expect that tension or compression to depend on the x value. Yes?
If you have width of a beam, would you see that like there's tension on the top and it's positive?
We're not going to do anything with the width. So yeah, we're going to assume that these are a lot longer than they are thick. That would, so really, so what would that affect here? It would not affect anything in this problem because those distributed loads are acting right down the center of the beam. So yeah, it wouldn't matter here. It is possible that if you had other kinds of horizontal distributed loads, it would change a little bit based on the thickness of the beam because you would actually have a moment arm. But if all you're dealing with is weight, then it doesn't come into it at all. Okay. All right, so Newton's second law says 105.27, 105.27 plus, I'll write this all as one force vector, 57.81x, 57.81x plus t negative v is equal to zeros. And so t is equal to negative 57.81x minus 105.27. And the shear force is positive 57.81x plus 105.27. Okay, so you can see that as you get closer to the midpoint of this beam, the magnitudes of the internal tension and the internal shear force are getting bigger. You can also see from this tension expression that all values are going to be negative, which means that this has an internal compression instead of an internal tension. Okay. That makes sense because the weight of this thing is compressing it. I guess also these two forces are tending to compress it, although they're doing other stuff too. And now the bending moment. This is the one that's a little more complicated to think through. So I'm still going to use this as my about point so that that first force vector doesn't produce any moment. The horizontal part of the distributed load doesn't produce any moment. The downward part of the distributed load produces a clockwise moment. So this is negative with a moment arm of x over 2 and a force magnitude of 57.81 x. And then we have plus m minus vx is equal to 0.
It's like always plus m minus vx.
Yes.
Right?
Yep. Unless you work from the other end, which I never do, but that's always an option you have. Okay, so m is equal to vx plus, what's this thing divided by 2? What is it? 28,905, yeah. Okay, so plus 28.905 x squared. And now we'll substitute in v. So m is equal to, something went wrong here. That's clockwise, so it's negative v okay.
A minus.
Yes.
Your 57.81.
Do you see where? Or, I mean,
like the vector, you have
yeah.
57.81x pointing down. But it's
Oh,
not.
oh no, because we already accounted for that direction by calling that a clockwise rotation.
Oh, sure. I was looking in the Newton's second law.
Newton's second law. Okay, so 57.
Like that 57.81 vector.
Oh yes, exactly. That's why. Okay, so v is, we have a negative there.
How did you notice your mistake?
Yes, because when you add up these, when you put in the v times x and add it to the term that you already have, you always get some cancellation of those terms. It's just because you have to satisfy those derivative relationships, and you're always, when you take derivatives, you're always dividing by numbers, making them smaller. Can you follow what I'm sort of roughly saying? So anyways.
You're saying because you got a positive.
Yeah, because the 28.905 and the Vx term
should be in opposite directions.
should be in opposite directions. Exactly.
Good question, Joe.
Yes. So m now is equal to negative 57.81 x squared plus 105.27 x plus 28.905 x squared. And so m is equal to negative 28.905 x squared plus 105.27 x. But if you hadn't noticed it when I did, you would notice it now when you did those derivative checks. dm dx, if I hadn't, if I'd left those signs the way they were, dm dx would not be equal to v. But now it is. Any questions about that first cut? And there's nothing new about the second cut. We just have a different set of point forces. So cut 2, this is for x values between 0.6 and 1.2. So over here we have the point forces of 105.27, 105.27. Now we also have this point force of negative 141.42, negative 141.42. The distributed loads show up the same way they did before. One thing to be careful of here is what's the distance between the left end and this point force? Nope. That's what to be careful of.
0.6.
Yep.
That's right.
It's just a fixed location. Like where our endpoint is doesn't affect the distance between the left end and that point force. So this is just 0.6. But what about these? So we still have a force this way of 57.81 x. And a downward force of 57.81 x. And what's this distance?
X.
Over?
2.
Correct. He said it slow so you could all get it in your notes. And then T, V, M. Okay, so Newton's second law. Guess I'll move it over here. We have 105.27. And then we have the other point force, negative 141.42, negative 141.42. And then we have 57.81 x, negative 57.81 x. Plus t negative v is equal to zeros. And so t is equal to negative 57.81 x plus, oh my God, that's not right. $36.15. V is equal to negative 57.81x plus, nope, this time it's minus 36.15. And then the moment equation, about point is over here. So we have negative x over 2 times 57.81x. I'm going to think of the vertical component of this point force. I'm just going to think of that as pointing down at 141.42. So that's another clockwise rotation. The moment arm is 0.6. The magnitude is 141.42. And then plus m minus Vx is equal to 0. And so we get negative 28.905x squared minus
84.85.
84.85 plus m minus Vx. So m is equal to negative 28.905x squared. That should be positive. Plus 84.85 minus 57.81x squared minus 36.15x. And so m is equal to negative 28.905x squared minus 36.15x plus 84.85. Okay. So can we sketch these? I think probably. So for the internal tension, we have a linear function that goes from negative 105.27 and then we can find the endpoint of this line by plugging in, where am I? Cut 1. So plug in 0.6 to that function. And we come down to almost exactly 140 negative. And then for the second cut, we start at basically 0. This is probably round off error. I'm just going to call it 0. And then we end up at negative 33. Point something. I'll just call it negative 33. So 2 parallel lines like that. So if your material is, I mean, you can't say too much about fractures and stuff until you do stress analysis, but you could look at this and say, okay, if my material is particularly susceptible to tension and compression, I would probably be more concerned about it as we move towards the center coming from the left side. Yep.
If you tried to preload a force onto that, would you shift the entire line up, or would it just be parts of it?
If you were going to preload this,
Because you can see that line is coming, or the jump is coming from the 200.
I mean, I guess, like, really you wouldn't do it until you did the full stress analysis, I think, you know? But if your only concern was this thing breaking in tension and the whole cross section was the same, yeah, I guess you would just put the whole thing into tension, and then that would just shift the whole curve up.
Like
Yeah.
we'd like tie a string at the center point.
Yeah, right.
Mm-hmm.
Yeah, right. Okay, so what about the shear force?
Where you are, we change things at all points.
Oh, sure. But
Okay, so what's this? Oh, this is also a linear function. That's nice. So this one starts at positive 105.
Yeah, that would be that.
And then goes down to $70.71. So from here to here. And then cut 2. Negative starts at negative 71. And goes to negative 105. Guess that makes sense. So again, those 2 lines are parallel, but there's just a jump due to that point force in the middle. And now what about these? Okay, so for the bending moment. So we're starting out with a positive slope, and it's going to be concave down, and it's going to start out at a value of 0. And it's going to be pretty close to it's going to be pretty close to horizontal when it gets there. And then the second one starts out with a negative slope. So it starts out with a value of 52. I didn't look to see where this one ended. They end at the same spot. Okay, well, I guess they end at the same spot because there's no point couple there. So they have different slopes. But, you know, so it's like a, what do you call that kind of thing? It has like a kink in it there, but not a discontinuity. And the value is 53, let's say. Yeah. Any questions about that? Okay, well, you can imagine, so we didn't even get to start one from a structure. We'll do one like that next time. But you can imagine, I mean, you just solve the structure, then you have the external loads on each one of those bodies, and then for each body, you do this. And one of the assigned problems is a structure that's like, I forget exactly what it looks like, but you have like a vertical one and a horizontal one. And it says to calculate the internal loads. What?
It's number 5.
Okay, yeah. Have I assigned that yet?
Yeah.
Okay, yeah. So you can do that by just, since it's all perpendicular, it's not too hard to just do those, the coordinate system transformations in your head. You're just switching, components from here to here and making some negative, some positive. But you can also do this with a positive 90-degree rotation matrix. Okay, that's all.
Can you do like a 30-second run through of how to do the rotation matrix calculation since I missed one?
Oh yeah,
You should make a function.
yeah. What calculator do you have?
TA84.
Yeah. Oh, let me. Does anyone else want to see that, or? Because otherwise, okay.
Is it like doable by hand?
Yeah, for sure.
Okay.
Yeah, just go into. So once you figure out, so you're always going from a coordinate system like this to, some new coordinate system, whatever it is. And so you have to figure out what the counterclockwise angle is. In this case, it would be a negative angle. And then, so every calculator, you enter matrices different, but just go to however you enter your matrices and just go, just make a matrix that's like, plug in whatever these values are. Okay. Then go to, go back to the calculation space and go this, just use the regular times function. And then however you define that vector in there, in this case, it would be,
Just do like the 200 point force or something, that's probably the easiest.
yeah, okay. So negative 200, 0, and it'll just spit it out for you.
Okay. So it's just a cross product then?
It's matrix multiplication, and
Okay.
but your calculator knows how to multiply matrices.
Okay.
It's like a series of dot products.
So it's just some weird like back and forth if you're to try and do it by hand, but if you
Yeah.
make a 2x2 matrix and a 2x2 matrix, it's simple.
Yeah, here's how it works. So the first element of this is A times E plus B times F. And the second one is C times E plus D times F. And if you just put it in your calculator using the regular multiplication function, and if they're sizes that are compatible, you can't multiply any two random matrices, but your calculator will do it.
Okay, but that's how you would.
That's how it does it, yep.
Product. Okay.
Right.
Cool. Thank you.
Sure.
Can the